In this lesson, we're introducing the idea of conditional probability. Let's start with an example to go through the basic ideas. Sue and Michael are about to each give a presentation. What is the probability that Sue goes last, given that Michael goes first? Let's look at it, first of all, without worrying about this condition. We know intuitively that there's a 50% chance of either Michael or Sue going first. If Michael goes first, then there's a 100% chance of Sue going second, and the same kind of thinking applies if Sue goes first. So if we work out the probability of Michael first and Sue second, the numbers will look like this. I usually prefer to convert percentages to decimals because the numbers just seem to be easier to work with. So the probability is 0.5 times 1 or 0.5, and of course you can present that as a percentage if you prefer. The same way would give us 50% for Sue first and then Michael second. But now let's look at the initial condition. If we know that Michael's already gone first, we start at this point. And so it should be clear to you that there's a 100% chance of Sue going second. This is the notation we use. We use a vertical pipe or a vertical bar symbol. This would read the probability of Sue speaking second given that Michael has spoken first, and we can see that the answer will just be 100%. In example 2, we're returning to the familiar two-way table idea, and this allows us to work with bivariate data or data with two variables. So first of all, we need to use the information we're given to complete the table. We have 100 students, so the grand total is 100, and it's always good to start by writing the total in. They were asked, do you enjoy mathematics? 75 students said yes, so we're along the total row at the bottom. 75 said yes, 6 were undecided, 53 of the students were male, and of those male students, 9 said no, and 35 female students said yes. Now you can see there we've got enough information now to go ahead and fill in all the other blanks just by doing a little bit of arithmetic. So let's look at the actual question. Here's the table again down the bottom for reference. Firstly, the probability of a respondent or a member of the class being female. Well, we have 47 females out of a total of 100, so that's a probability of 47%. B, the probability of someone being against. That's a no vote, and there are 19 people out of 100 who voted no, so that's a probability of 19% of someone being against. C, the probability of someone saying yes and being male. So we need to look at this a little bit more carefully. You'll realise that this is a point of intersection. There are 40 people who are male and said yes, so the probability is 40%. Now it gets interesting. The probability of someone being against or female. So now we highlight this row and this column. There are 47 out of 100 who are female, and there are 19 who said no. So what's the probability of someone being against or female? Note that they can be male as long as they voted no. You'll see here that there's another point of intersection, and we need to be careful we don't count this number twice. So the probability will be 9 of the males who said no plus the 10 females who said no, added to 35 who are female, and 2 who are undecided who are also female, but we're not counting that 10 twice. It's out of a total of 100, and that gives us a probability of 56%. Another way of looking at that one is to use this rule. The probability of two events, A or B, is the probability of A plus the probability of B. And as we said before, where those two sets intersect, we must not count the number twice. So in fact, we need to subtract the intersection. Or can be replaced with the union symbol using set notation. And remember that intersection is the same as AND, where sets A and B intersect is events A and B both occurring, and union simply means A or B occurring. So again, let me highlight the information we're looking at. A person can be female or vote no, and the intersection is 10. So let me just write A and B so that we can relate it to the formula. So now the probability of A or B is 19 out of 100 plus 47 out of 100, and then we subtract the 10 out of 100, and that will give us a probability of 56%. So you may prefer to use that rule if it's not obvious to you how to do it straight from the table. So now we look at the first example that has a condition on it. What's the probability of someone saying yes given that they are male? Now, if we're given that they're male, we're no longer working with 100 people. We're working with 53 people. So this is a subset of the original sample space. So they have to be male. They're voting yes. 40 people who are male voted yes, but the total is 53 males. So the probability is 40 over 53, which is approximately 75%. You must not divide by 100 because we're not working with the total number, which includes females. We're only working with the males. That's the condition on the problem. Similarly, what's the probability of someone being male given that they voted undecided? Alright, so that we're in the undecided column and we're looking at males. There's 4 of them, but the total number of people who were undecided is just 6. So the conditional probability is 4 over 6, which is about 67%. Hopefully you can see that the numbers we get are quite different when we have an initial condition. This is because instead of working with the original sample space of 100, we're working with a reduced sample space or a subset of the original sample space.